Welcome back. In the last lecture, we were discussing the steady state heat equation, or in other words some Laplace equation, which is delta of Laplacian of u, which is defined to be u x x plus u y y. Now, we are considering it in the domain, which is the upper half plane, and the boundary of that domain is the real axis, where y is equal to 0. And this is the equation what we considered is delta u is equal to 0 and u x 0 is f of x, and we are assuming our f to be nice function in particular source space. Then what we have seen is that u of x t is given by so u of x y, this is, or this is p t of, this is f convolution of p y of x, where p y of p y hat at xi is equal to e to the power minus 2 pi mod xi y. So, now we would like to find out what is the function for y greater than 0 xi is in R. What is this p y such that p y hat of xi, this is equal to e to the power minus 2 pi mod xi y. So, obviously, what we would like to do is to take the inverse Fourier transform. So, we will write p y of x, this is equal to minus infinity to infinity e to the power minus 2 pi mod xi y, and then e to the power 2 pi I xi x d xi. This is equal to, we can write this as 0 to minus infinity to 0 e to the, because there is an involvement of modulus of xi. So, it is wise to break this integral into the negative part, negative xi and positive xi. So, what we will get 2 pi, this is minus means this is minus of xi. So, 2 pi of xi, if I take it outside, this is I x d xi. This is simple. So, if y is not equal to 0, so y plus I x is not equal to 0, and this integral what we know is that e to the power 2 pi xi y plus I x divided by 2 pi y plus I x, this is minus infinity to 0. Now, at xi equal to 0, so this is going to be 1 by, this is no xi, at minus infinity this is going to be 0, and then plus we have 0 to infinity e to the power minus 2 pi xi. If I take this outside, then what we have got y, and plus is minus of I x, and this is d j, and this part is going to be plus e to the power minus 2 pi xi y minus of I x divided by 2 minus 2 pi y minus of I x, and this is 0 to infinity. At infinity again it vanishes, only thing what it survive, this is going to be at 0. So, this essentially is going to be, one can write y by, going to get, this is y by x square plus y square. Okay. So, just simple verification of that, and so this is our p y of x, this is equal to this is a factor of pi is going to be there. So, 1 over pi y by x square plus y square, this is called the Poisson kernel. Okay. So, now we want to, what we have seen is that for each such y, we are going to get that this is f convolution of p y at x. So, now like in the heat kernel case here, we will also rely on the fact that this Poisson kernel is a good kernel. So, in order to check that whether it is a good kernel or not, so let us first property is that p y of x, this is greater or equal to 0, because y is greater or equal to 0, hence this is greater or equal to 0. Now, the second one is that if we compute minus infinity to infinity p y x dx, this is equal to y by pi, we can take this out, minus infinity to infinity, this is dx by x square plus y square, and this is an known integral, this is 1 over a tan inverse of x by a, this is equal to certainly 1 over pi into pi by 2 plus pi by 2. So, this is going to be equal to 1. So, this is also very easily verified. Now, for delta greater than, for any delta greater than 0, let us look at mod of y greater than delta p mod of x p y of x dx. Now, in terms of the x, we know that this is going to be this is an even function. So, therefore, we can write this integral as delta to infinity p y of x dx. Okay. So, now this is delta to infinity y by x square plus y square dx. Now, substitute, put u is equal to x by y, then for each fixed y, then therefore, du is equal to 1 by y dx. So, this becomes 2 by pi, this is 0 to if y x is equal to 0, this is 0, infinity infinity. So, now this is y into dx is y du. So, divided by this is x square is u square y square plus y square. So, this is equal to 2 by pi this is delta to infinity, this is 2 by pi, and then integral delta to infinity du by 1 plus u square, which is equal to 2 by pi tan inverse of u, and this is the delta to infinity. Now, so this is going to be equal to, so now this is pi by 2 is this is 2 by pi. So, this is 2 by pi into pi by 2 minus tan inverse of x by y, and oh sorry, this is, if I am making a change of variable, then this is delta y. So, this is delta by y, delta by y. So, this is delta by y. So, as y goes to 0, if y goes to 0, then tan inverse of delta by y, this converges to pi by 2. So, this converges to 0 as y goes to 0. So, this shows that, so this implies p y x is a good kernel. So, now we can use the properties of the good kernel, in the sense that if our f is in the Schwarz space, then what will be the solution of this Laplacian equation or steady state heat equation. So, let us, just like the earlier case, we can utilize the properties of the good kernel. So, the theorem, let us write it down, that let f belongs to the Schwarz space and u x y is equal to f convolution of p y at x. Then u is in C2, and then what we can do, R2 plus, that is R2 plus is the upper half plane. And this satisfies, we have verified that this satisfies this condition. So, this is the equation of this. Now, about the boundary, what we know that u of x y, because f is a continuous function, converges to f of x uniformly as y goes to 0. Then the third, like in the heat equation, also u x y converges to f in the square mean, that is minus infinity to infinity u of x comma y minus of f of x square dx. This converges to 0 as y converges to 0, just the use of the Planck's rule. And fourthly, if u of x, the boundary value is f of x, then u actually is a continuous function on the closure of our upper half plane, including the boundary. This is a continuous function, that is, and also not only that, this is also goes to 0 as we go towards the infinity. That means u of x comma y, this goes to 0 as mod x plus y, this converges infinity. So, this is the proof is more or less exactly the same as in the heat kernel, because of the Poisson kernel is a good kernel. Now, one of the interesting feature which is a pretty useful class of function, any real valued function. If u is equal to 0, then u is called harmonic function. This is a pretty rich class of function and which has some very nice properties and they are very useful to study. So, in this lecture we would only discuss one beautiful property of this harmonic function, which of course we have encountered in the Cauchy-Riemann equation when we do the complex analysis. So, this one very useful property is that we can actually capture this function by knowing the values. Suppose I have a point x y in the upper half plane, I have x comma y. Now, you given to me that u is harmonic, and then by knowing the value of u on this boundary, I can determine the value of u inside point. What precisely what does that mean? And this is called a mean value theorem. So, it says that you can take let omega be an open set in R 2 plus, and delta of u is going to be equal to 0. Now, let x y belongs to omega. Now, if consider the disk, that is the set of all let us say p and q in R 2 such that distance of p and q with x y, this is less than r, and then the d closer if I take, then this is less or equal to 1. So, obviously, there will be a guarantee that because omega is open, take any x comma y in omega, then I can get a ball around the x comma y centered at x comma y, which is going to contain entirely inside omega. Not only that, I can get a ball whose closure is also contained there. So, now if I take such a ball, then u of x comma y, this is equal to 1 by 2 pi 0 to 2 pi u of x plus r cos theta and y plus r sin theta d theta. That means, this represents what? This represents the circle with the radius centered at x comma y, and this is r. For all 0 less or equal to or less than r. So, now the value if I know on the circle, then and I know that u is harmonic inside the disk, and this is then what we can get is that we can capture the value of pointwise value by just taking the average over all the values on the circle. So, that is why it is called mean value theorem for harmonic function. So, as you can see that x plus r cos theta and they are the and y plus r sin theta, they are the points on the boundary. So, now for the proof, let us denote this u tilde of r theta, this is equal to u x plus r cos theta y plus r sin theta for each fixed x comma y. Okay. So, now what we know, I mean we know that delta of u tilde, and what is the, if from the Cartesian coordinate, if we are writing the Laplacian in polar coordinate, we know that delta is equal to del square by del r square plus 1 by r del by del r plus 1 by r square del square by del theta square. This we know. So, what do we want to prove? That the, so want u of x comma y is equal to 1 by 2 pi 0 to 2 pi u tilde r theta d theta. This is what we remember, that u tilde depends on x and y. So, we are fixing one x and y a point. So, we can afford to not to mention in the symbol. So, now this equation, if I apply the Laplacian into it, so let us write down the r square del square u tilde by del r square plus r times del u tilde by del r plus del square u tilde by del theta square. This is equal to 0. I am just multiplied the r square because delta of u tilde is equal to 0. So, this if I write this, this is going to be, if I take r del by del r of r del u by del r del u tilde by del r, this is equal to, if I take, then this is going to be r squared del square u tilde by del r square, and by this is r times 1 into del u by del r. So, these two quantity can be written as this. This is minus of del square u tilde by del theta square. Okay. So, therefore, what we want is that f, if I denote f of r, this is equal to 1 by 2 pi 0 to 2 pi u tilde r theta d theta. This what we want to get is that u of x y, u of x y is nothing but u tilde of 0 theta if you are taking, then this is equal to u of x comma y. So, now essentially we want whether this is equal to f of 0, that is what we intend to. So, for that, that means if I want to say that the f r is equal to f of 0, which means it is a constant, that is what we would like to conclude, then for that definitely if we can show that del f by del r, if this is 0, then we are done. So, now if we do this, so in order to show this, so now what we have, as you can see that this is true. Therefore, if I take the integration both the side, so this will imply that 1 by 2 pi, then I take the r, then integral 0 to 2 pi del by del r of r del u tilde by del r d theta. This is equal to minus of 1 by 2 pi 0 to 2 pi del square u tilde by del theta square d theta. Now, simply from this what we can get is that this is r, we can pull out from the last expression, this is equal to r, then this is 1 by 2 pi, this is 0 to 2 pi del u tilde by del r d theta. This is equal to integral of del square u by del theta square, which is a 2 pi periodic function. So, this is going to be equal to 0. So, now this is nothing but r times del by del r into r del f by del r, this is equal to 0. So, now once this is equal to 0 means del by del r of r del f by del r, this is equal to 0 because this is true for every r. This implies that del f by del r, this is equal to some constant. Now, for r equal to 0, we know that this is equal to 0, therefore, this will imply that del f by r del f by del r, this is equal to 0. This is true for every r, then del f by del r, this is equal to 0. This implies that f of r is constant and f of r is equal to f of 0, which is nothing but u of x y, and that is what we wanted to find out. So, now what it says that if I have a harmonic function, then I can take the average on the circle and I can get the value inside the circle. So, this is a very good observation and very powerful tool to work for the with harmonic function. So, in the next lecture what we will be doing is that we will see some more applications of the Fourier transform vis-a-vis in PDE and in statistics or in physics and engineering. Thank you.